there's also a very interesting phenomenon associated with all sound waves, but particularly associated with the sound wave, because if we talk about audible sound, it is very noticeable. In 1842, an Austrian physicist called Christian Johann Doppler called attention to the fact that the color of a luminous body, let's say light, must be changed by relative motion of the body and observer. Say, for example, if the source is a red light. Say, for example, if it moves at a certain speed, let's say very high speed, with respect to an observer, then the color will change. That sounds very weird, but that happens. For example, that according to the Big Bang theory, that our universe expands at enormous amount of speed. The further the galaxy away from our solar system, the faster the speed moving away from us. Well, all the stars is actually burning gas ball. Let's say it burns hydrogen. Hydrogen has a particular spectrum, and we know that for the red light is what is the wavelengths, say for example, or frequency and wavelengths is associated. So we observe, let's say we pick a distant star, and we get the starlight, and we notice that the frequency actually decreases. Frequency decreases, that indicating the wavelength increases. So the red become more red. This is called red shift. Now, if somebody say red shift, that actually means the source is moving away from us. The other part of it is if the source is moving towards us, we call it blue shift. So if next time you hear the term red shift, which means the source is moving away from us. Now, let's take a look at what happened. Let's use the example of a sound. For example, this is source, and the source is at rest, and the circle represents the wave front. And so during delta t, the first wave front reached here, and the second wave front 1 period later reached here. So the definition of two consecutive wave fronts, that distance is 1 wavelength lambda. Since the source does not move, so the wavelength does not change. Three-dimensionally, it's symmetrical. Here's the observer. Let's say observer moves towards the source at v of o. O means the observer speed. Now, sound spread at a speed of v. We just learned that speed of v is associated with the temperature of the fluid. In this case, the temperature of the air. So if the wavefront traveled to the right with a v, the observer traveled to the left with a VO. Isn't that true? The relative speed of the observer and that wavefront is v plus a VO. This is the relative speed. Now we learned that the frequency received by the observer is its speed of the wave divided by its wavelengths. Since wavelengths doesn't change, but the speed of wave sounds like changed, because you see from the point observer view, if we assume observer doesn't move, then the wavefront actually approached observer with this speed. This is the relative speed. So if we replace this v prime relative speed between the source and observer, which is that, and we replace the original wavelengths, well, it doesn't change. Therefore, that is original speed divided by its frequency. What we get is the new frequency received by the observer. It is the original frequency of times v plus v of o over v. Here, I want to point again, this v is speed of sound. Speed of sound. That's v. That o is speed of the source, move towards sound. Well, obviously in this case we use the ground as reference because all the speed has to be related to something. So the source does not move, and observer moves with respect to ground to the left and VO. So with respect to the wave front, that relative speed is the v plus VO. So if the original source frequency is f of O, now the frequency received by the observer is more than FO because this ratio is more than 1 right now. This tells us, for example, if this is a siren of frequency 1000 Hertz. If the observer drives a car, travel towards the siren at a very high speed, then the observer will receive a higher frequency. That means a sharper pitch. So you can imagine if the observer moves away from the source, then it will experience a lower pitch because the relative speed now will become the V minus VO. And then here will be a minus sign. So then experience a lower pitch when the observer is moving away from the source. This is so-called the Doppler effect. I would like to show you the picture from the transparency that this is the source, it is at rest. Therefore, how can you tell it's rest? Because did you see the wave fronts? All the circle has the same wavelength left and right. And this is the observer, which travel towards the source with a VO. This is the case we discussed. Imagine this bicycle actually travels towards the other direction, then it's leaving the wavefront. So relative speed will be V minus VO. Now the second case is very interesting. If you take a look at the purple dot, that is associated with the first wave circle. That's the first wavefront. And then the green one is associated with the green dot. What does that mean? That means the source moves from initial position to the green one, that's the next position. Then the yellow one is associated with the yellow circle, which is the yellow wavefront, and the red is the last. So because when the source moves, now for observer A, the wavefront looks like compressed, that is lambda of prime. So for this person, he received a shorter wavelength. Now, the frequency of the source does not change. So therefore, this person, but this person received a shorter wavelength. Speed of sound is still the same. So for this person, he will experience a higher frequency because what he received, the wavelength is shortened. It's not as before. But for observer B, you can tell the wavelength now is longer. Now look at this. Speed of wave is wavelength times frequency. So if the speed of wave does not change, say for example, observer A experienced a higher, I should say, a shorter wavelength, which is lambda of prime. When this one's shorter, and then obviously if you want to get a frequency will be higher since V is a constant. For observer B, if wavelength is longer, then only when the frequency makes smaller, then V will be constant. This is also called the Doppler effect because frequency changes. But this is the case is due to the shorten or lengthen of the wavelength itself. Okay, mathematically, how do we get the relationship of the new frequency associated with the original frequency due to the motion of the source? Let's say the source moves. That's S. Source moves, in this case, to the right with a Vs. Be careful. This has nothing to do with speed of sound. Speed of sound has something to do with, obviously we know that the Book modulus of the air and also the temperature of air, this and that. Okay, so it's different. Speed of sound is still as V. That Vs means speed of source. Now, as we remember, for observer A, the wavelength gets shortened. So how much shorter? Original wavelength is this. It gets shortened by this much. How much gets shortened? That is actually due to the motion of the source. The source moves at this within 1 over F is delta T. That is 1 period. Within 1 period of time. Because imagine This is the first wavefront. The second, if the source does not move, the second wavefront is supposed to be here. So this is the original wavelength if the source does not move. Now, if source moves this much, that is V of S time that one period of time. Then the wavefront comes here. So isn't that true? Get shortened this much? This much is speed of source time t. That is speed of source divided by the frequency, because 1 over f is t. So we get that. And if we replace everything, that is at lambda prime, we can replace with that because we know f of prime equals to v, speed of sound still constant, over lambda prime. So we get that v lambda prime is lambda minus vs of f. If we rearrange everything, the result comes out as new frequency due to the source move equals to v, speed of sound, v minus vs, vs is speed of source, and time the original frequency. So for observer A, frequency increases because this ratio is more than 1. For observer B, you can imagine because the wavelengths lengthen and then the frequency should drop. So if we consider frequency drop, this become a plus. So let me combine that equation.